you ever heard those commercials for diabetes medication where they say, like, ask your doctors about your A1c level and that sort of thing? Well, the reason why they do that is because hemoglobin A1c levels are an indicator of how well somebody's blood sugar has been controlled over the last several months. An advantage over just like a snapshot. So just like if you were to just measure someone's glucose to their blood sugar levels at like a single point, well, that would be like heavily influenced by whether they just had a big meal or something. So if you want to see what the blood sugar levels are like chronically, like over the last few months, maybe you even want to see if these levels have been like increasing or decreasing, this A1c is super helpful. But like, what actually is it? Well, it is a form of glycated hemoglobin. Okay, so let's break that down. So hemoglobin is the protein in your blood cell, your red blood cells, that carries oxygen. So typically that's what we think of hemoglobin's importance or whatever. But hemoglobin, it turns out, can also get modified. And it can get modified by glycation. And so glycation is where you have a sugar molecule stuck to something, and it happens in a non-enzymatic fashion. So we call it glycosylation if you have a sugar chain attached enzymatically, so with the help of an enzyme, so typically like a protein that helps mediate the reaction, like bring the reactants together and make it easier for them to combine. Glycation is non-enzymatic, so it just like spontaneously happens because of the chemistry the sugar chain gets stuck on. And so this is actually sucrose, so sugar, glucose plus fructose, which gets broken down into glucose plus fructose in your cells, and the glucose is like what we call blood sugar. So blood sugar is glucose, and the sugars can get like interconverted and stuff. So but when we're talking about blood sugar, we're talking about glucose, but my sugar packets are sucrose, but just go with it. So if you don't have much sugar, this isn't really likely to happen, this spontaneous sticking on of the sugar. And when I'm talking about sticking on, I'm not talking about like just the temporary interactions where something binds and it unbinds. Instead, I'm talking about like stuck, like permanent stuck. Like take some Scotch tape stuck. Except we're not even talking about Scotch tape levels. We're talking about like super glue, okay? So basically stuck on. And this has consequences because since it's not coming off, the more these chains get glycated, the more these hemoglobin proteins get glycated, the more these cells fill up with glycated hemoglobin. And so these levels aren't gonna, so overall you're getting a sense of the like chronic blood sugar levels. So these blood cells typically have a half-life, or a lifespan of about 120 days. So the sugar levels, the A1c levels, they're going to tell you about the sugar levels over the past several months. And you can think that, so you have like 200 to 300 million hemoglobin molecules per blood cell. Your red blood cells are basically just like hemoglobin like factories, and they just like chock full of hemoglobin, and the hemoglobin is going to hold on to that oxygen, so it's really important. So typically you have like 4 to 6% or so of your hemoglobin will be glycated in like a healthy person. But in people with diabetes, they have higher blood sugar levels over time, and so they're going to have more hemoglobin get glycated. So because in diabetes, what happens is, so in like type 1 diabetes, your body doesn't make enough insulin. It's like an autoimmune thing where your body is like attacking the insulin making cells, and so then you don't make enough insulin. And in type 2 diabetes, your cells are like resistant to insulin. So even though you can make it, your cells aren't getting the message very well. Why does this matter? Okay, so insulin is basically, it's a hormone that tells your cells, and well, it tells them a variety of things, but one of them is to let in glucose. And so to let in blood sugar. So if cells can't let in blood sugar, then the blood sugar levels are going to rise because it can't get into cells, so it's going to stay in the blood. And the blood, so how it does that is because, like, so the insulin receptors, they, so the glucose transporters, so you have different glucose transporters. And so the blood cell, your red blood cells, they have a different glucose transporter that doesn't rely on insulin. So this is why if you have high blood sugar levels, you're going to get high amounts of glucose in the red blood cells. And when you have high amounts of glucose in your red blood cells, sorry, I need more tape, then they're going to stick and you're going to get more of this glycated hemoglobin. So you're going to get a higher hemoglobin A1c level. But in the rest of your cells, well, most of the rest of your cells, they use a different glucose transporter. So a glucose transporter is what's going to allow the glucose to get through the cell membrane. But so the red blood cells, remember, they're using a different transporter, so they don't need the insulin. So that's why you can get these high glucose inside the red blood cells. But in your other cells, they rely on a different glucose transporter. And so typically this glucose transporter, so remember we want it in the cell membrane in order to let in glucose. But when you don't want to let in glucose, like if there's no glucose around or you just don't want, your like cells are like, I've got enough glucose, then you won't have the glucose transporter in the membrane. And so instead it's hanging out in like an intracellular like membrane, like a vesicle. So because this protein likes to be in membranes, and because you want to have it like pre-made, so you can like put it into the cellular membrane really quickly, you can have it in this like intracellular vesicle. And then upon getting the signal from insulin, then that vesicle can then insert it into the cellular membrane to let in glucose. And so if you don't make enough insulin or you're not responding to insulin, then you're not going to be letting in the glucose. If you're not letting in the glucose is going to build up in the blood. If the glucose builds up into the blood, it's going to get into these blood cells. If you have a lot in these blood cells, you're going to get a lot of hemoglobin A1c. And so people with diabetes, they typically have higher levels. Basically, if you can kind of see, by tracking the A1c levels, you can see like whether someone with diabetes is controlling their sugar levels well, whether someone is like progressing from pre-diabetes to diabetes or reversing the trend for like type 2 diabetes. I'm not going to get into the medical stuff. Disclaimer, I am not a medical doctor. I am the geek kind of doctor, finally. So I'm going to stick with what I know best, which is the biochemistry. I'll tell you about the biochemistry happening in this process because it's really cool. So basically it involves this glycation, which is actually similar to the mechanism that happens when you like cook meat and you get that like browning. It's called this like Maillard reaction. And basically it first involves something called the Schiff base formation, which we've looked at a little before. We'll talk about that more here. And then that's followed by this rearrangement, this like Amadori rearrangement. And that rearrangement is going to make it so that it's like irreversible. So basically that Schiff base formation, we've talked about it before, and it's really helpful because typically like a lysine, or in this case like the N terminus of the protein, so the very end, it has this amino group, so this nitrogen attached to hydrogens, and it can do this thing called form this thing called a Schiff base, where basically it sticks on to, it like replaces a C double bond O. It replaces that O with like the nitrogen in that group. And so now you have the thing stuck on. And we've talked about Schiff bases a lot with like enzymes and stuff, because it's really helpful because it allows these, typically the lysine residues, to hold on to a group in order to like hold it in place for like enzyme reactions and cofactors and that sort of thing. And it's important there because it's reversible, and so you can swap out the things. But with this Amadori reaction that happens, you actually get this movement of the electrons. So you're going from the Schiff base, where you have like a double bond between the carbon and the nitrogen, which is still able to react, and you're making that into a ketone. So you're taking that double bond that was going to the N, and now you're making it go to the O. But basically, the end result is that you can't undergo like reaction with the Schiff base reversibility. So although that first step is reversible, the second step, so the Amadori reaction, is going to make it so that this change is basically permanent. And so over time, your cells are building up more and more of this. And remember, the more and more sugar you have, the more likely this is to happen, because these are non-enzymatic processes, so they're just like spontaneously happening. So these molecules have got to be like in the right configuration and everything. They've got to be bumping into each other. The more you have, the more likely they are to bump into each other, not relying on any enzymes or anything. So what really important is the concentration. And so the more sugar you have, the more H1C you have, and this is going to build up over time. Because these cells have a half-life, or not a half-life, they have a lifespan of several months. It's going to tell you when you take like a snapshot and you look and see like the percent, like what percent of the hemoglobin molecules are glycated. Then you're going to get an idea of the like the past several months. So even though you have new blood cells forming and dying and forming and dying or whatever, overall you're going to get a sort of snapshot of the last few months. And yeah, so I'm not going to go into the medical stuff because, one, I don't feel like confident enough, and then there's also that there's some like controversy over various aspects of it and how well it represents various things. But I want to tell you about the biochemistry of the reaction, as well as some of the tests for it, like how they work. And I think so these products, they can actually have harmful, like toxic effects. But your cells actually have like receptors for like glycation products, like advanced glycation end product receptors, or like RAGEs, and then they can do all this like signaling stuff and cause problems. And so yeah, so there are effects of the glycation, but I'm not going to talk about those effects here. I'm just going to focus on like how they form and how we measure them, and why that matters.
So I'm going to start with like a more general audience type, and then I'm going to get really geeky into it in terms of like the actual mechanisms of like all the formation stuff, like drawing out, arrow pushing and everything. So just to warn you, and to give people that want that a chance. So that's gonna be at the end, so that I don't just like bore people or scare them away. Okay, so let's talk about what we're talking about. So we're talking about this hemoglobin, and so it's this protein that transports oxygen throughout your bloodstream. And so it actually has these 4 chains. So proteins are long chains of amino acids all folded up. And you can have multiple chains forming a protein, or proteins can just be a single chain. In this case, it has 4 chains. So it is a tetramer and it's a heterotetramer. It has two alpha subunits and 2 beta subunits in our main hemoglobin, our main adult hemoglobin, HbA. And then each of those holds this heme group, which has this iron, and this is actually going to coordinate to the oxygen, and it's going to travel throughout your blood. Okay, so this is what hemoglobin looks like, but what it does, but what we're going to talk about is how it gets modified. Our players are this hemoglobin and the glucose, and so I'll get more into this all. But what's basically going to happen is that the N-terminus, so proteins are like chains of amino acids. And so at one end, you have the N-terminus, which has this free amino group. And at the other end, you have the C-terminus, which has this free carboxyl group. And so we're talking about the N-terminus. So we're talking about the very end with this H group. And what's going to happen is it's going to get stuck to the glucose, and you undergo this thing called a Schiff base formation. And then that's going to rearrange to give you this this product. And so this reaction is fairly reversible, but this is not. So this is basically pretty much permanent. And your red blood cells have a lifetime of about 120 days. And so this, if you look and you measure the amount of like the fraction of the hemoglobin of a person's hemoglobin that is glycated, that'll give an indication of like how well their blood sugar is controlled. And so according to the CDC, like normal is below 5.7%, pre-diabetes is 5.7 to 6.4, diabetes is 6.5 or above. Although there are some caveats and stuff to this method, and I'm not going to get into all of that. But yeah, so we'll go more into the details of this. But the reason why I say like HbA1c in its strictest definition or whatever. So where does this HbA1c name come from? So you might think that it comes from the fact that it was happening on like the A chain, but that's not it. It's actually happens on the B chain, the end of the B chain. And so it's important to note that this reaction, glycation, like it can happen to and like other places on the protein, and other types of not just like a glucose added, but HbA1c in its strictest definition refers to when you have a glucose being added to the valine at this at the N terminal. So valine is one of the protein letters, so at the N terminal of the beta chain. And so that's where does this definition come from? So according to this good review article I will link to, so HbA1c is yeah, so here's where that definition. So basically normal adult hemoglobin, there's so HbA is the main form, which has those two alpha and two beta subunits. There's also HbA2, which has two alpha and two delta subunits, so delta instead of beta. And then there's fetal hemoglobin, which is primarily in like the fetus, and has a higher oxygen affinity, so that the growing fetus can grab oxygen from the mother, and then after they're born, then they start making the adult hemoglobin. But anyway, okay. So about 6% of the total of the HbA, so that's like the normal one with the 2A and 2B. So about 6% of that is termed HbA1, and that has these subfractions 1A, A1, A2, B1, and B2. So basically about 6%, like we'd seen, so 6% that would actually be like pre-diabetic, I think, depending on that. But basically, it's a sub portion of HbA, which is the main hemoglobin. So it's not referring to the A chain, alpha chain, it's referring to HbA as in the adult hemoglobin. Okay, and where this, where the A1, or where the 1A, comes from. So there's this paper. So basically these groups had found out that there were different, their mixture of like hemoglobin was heterogeneous. So it wasn't like one product. So the product seemed to have like some modifications or something that was and they knew this because it was the portions were running differently in something called ion exchange chromatography. Ion exchange chromatography, basically proteins have different charges because their proteins have these unique combinations of letters, so amino acids, and some of those can be charged sometimes. And since different proteins have different combinations of letters, so some will have more charged than others. And we define a value called the PI, the isoelectric point, which is the point at which like a protein is neutral. But basically, since proteins will have different charges, and this is actually pH dependent. And so this is because the pH is a measure of proton availability. And so at a lower pH, you have a higher concentration of protons, and so things are more likely to be protonated, and vice versa. And so the pH is going to affect the charge of the protein and how it'll run. And so if proteins have modifications that change their charges, then you can separate them, the different versions of the same protein, using some chromatography methods. So there was actually, before this group, there was a group that had found that using like starch electrophoresis, so separating based on charge, not through chromatography. So chromatography is where we separate something based on differences in like some property as the things are moving through some sort of like solid support, typically, or like a gas or something that's impeding their movement or that they're traveling through and that they can interact with. And then because they'll interact with it differently, they'll travel through at different rates. So with electrophoresis, you're actually using charge to get things to move. With chromatography, it relies on other methods like gravity flow or pumping or that sort of thing, but it's not like the charge is getting them to move through something. But this group had found that when they use their electrophoresis, so here you're actually using a charge to motivate things to go through, they found that there was a fast moving fraction. So this suggests that since they were electrophoresis is typically run towards like a positive electrode, so more negatively charged things are going to travel faster. And they found that there was this fast moving fraction. And sorry, I can't show that, but that paper, I couldn't find like the actual paper, just like a citation for it. And then people talking about it in other papers. So there was this fast moving fraction. And then this group was actually able to like further separate the fast moving fraction using different forms of chromatography. And so you can see this is like re-chromatography. So basically they did their chromatography and they found this fast moving fraction. And then they further separated it. So they took this fraction and they ran it through more chromatography columns, but they did it when they were changing the pH. And so when they changed the pH, the proteins would run at different volumes. And so by changing it just a really little bit about the point where those proteins will start to differ their charge, they were able to separate these various fractions. And this is where you get the A1A, A1B, and A1c. And so the C was the third one. And so this is what is referred to as the A1c. And then later they found out that that was because this fraction had the glycation at that N-terminal valine of the beta subunit, the beta chain. And then these other ones were different glycation products. But anyway, so that's where the name comes from. And so how does this reaction actually happen? So I'll get into the exact mechanism like in depth in a minute, but it involves it's like a nucleophilic reaction. So basically atoms are made up of protons, neutrons, and electrons, and these electrons are these negatively charged subatomic particles that whiz around this dense central core where the protons that are positively charged are. And the electrons of different atoms can interact to form bonds. And so the protons, so this nucleus, like how tightly different atoms hold, the protons can rein in those negatively charged electrons, depends on the different atoms. And so some atoms we call electronegative, which means that they pull really tightly on those electrons. And this can make them partly negative, and the thing that they're attached to partly positive. Atoms can also have like lone pairs of electrons, which as we'll see are going to come into play. But basically, if something is, you can think of like, if something has more electrons than its nucleus can really handle very well, it's going to want to share those electrons. And so where it's going to find help for sharing it is in the nucleus of another atom. And so we call these nucleophilic, and they're typically like often things with like a lone pair of electrons. And so we'll see that our nucleophile is going to be the end of the protein chain. And then electrophiles is the opposite. They want electrons. So they often have like a partial positive charge or a full positive charge. And basically they're looking for electrons. And so they're a perfect match for a nucleophile that's looking for protons. And so what we're going to see, okay, so in our reaction, we have this amine, so this NH group, it's going to be reacting as a nucleophile. And so this pair of electrons is actually going to attack this carbonyl carbon. And so we call this a carbonyl when it has a C double bond O. This is more specifically an aldehyde because it has a C double bond O bound to just an H. And so because the oxygen pulls really hard on the electrons, it's very electronegative, this is going to make this partly positive and electrophilic. And this is nucleophilic, and so we get this attack. The electrons and the protons and stuff shift around a little, and you end up with, now you have a double bond between this the carbon and the nitrogen, and we call this an imine or a Schiff base. And then this can undergo a rearrangement. And so now we have this movement. So now here we had a double bond between the carbon and the nitrogen. And here we have a double bond between this carbon and this oxygen. And so now we have a ketoamine. So this is a ketone. So before we talked about the aldehyde had a double bond O with an H, and then the ketone has a carbon on either side. So instead of having an H on one side, it has a carbon on both sides. And so this is a ketone, we call that a ketone, and this is an amine group, no longer an imine group. And so now we have this ketoamine, and this is actually going to recyclize, because remember that glucose is typically in like the circular form, so the cyclized form, but it's going to cyclize a little different than it was before, because now you have this carbonyl here. So what's going to happen is like this end hydroxyl group can attack here, and then that'll convert to an OH, and you'll have this ring product. And so you can see like this ketoamine is a lot more stable than this Schiff base. So now this nitrogen's pretty happy, and it's not going to be anywhere near as reactive. And so over time, you're going to just be building up glycation. So you're not going to be removing it. And since these blood cells have a half-life of about 120 days, that's going to explain why it's going to show you like the past 2 to 3 months blood sugar levels. But these products can also be further modified and to like produce advanced glycation end products, or like age. And so these products can then like serve as bind to receptors and cause problems, and they're kind of like a signal that something's wrong. There's like stress and stuff. So yeah, so there's a bunch of that. As to how the actual like amidori rearrangement part is, so I'm not really going to go into that part. I'll go into detail about like the Schiff base formation and the basics of this, but for the amidori rearrangement, so like I said, how it like recyclizes or whatever. So this is from Wikipedia, author credits Smokefoot, but you can see that this is all like the reaction, the interconversion, and all this is happening in the open chain. But then at the end, you have this recyclization. And so this is going to be the part, so it's kind of like upside down to where mine was, but this is going to be the part that you're attached to your hemoglobin. So as I mentioned, it's often measured as an indicator of like glucose control in like people with diabetes or prediabetes. And so how is it actually measured? So there's some different methods. So some of them rely on ion exchange chromatography. Typically, so like often with like HPLC, so high performance liquid chromatography, which is and so they use this basic subcharge. So remember that the glycation is going to alter the charge, and so you can separate the products that way. Others use like a different form of chromatography, so like affinity chromatography. So in affinity chromatography, you're getting something stuck to your the like separator thing, and then you're going to, so it's be like you have resin, you're going to get your thing stuck to it specifically. So your resin is specific for the thing that you want to isolate, and then everything else is going to flow through, and then you can elute, so like push off the thing that was bound. And so this is actually done with this like boronate affinity. So it turns out that, where did I put that? So it turns out that this like boronic acid or whatever, so it has these 2 OH groups, and this the sugar product has these 2 OH groups, and they can actually react to form this product, and this will get it stuck onto the column, and then you can unstick it afterwards. And so there's various methods that use this sort of thing. There's also immunological, like immunoassays. So basically, so antibodies are these little proteins. So you typically talk about them often in terms of like disease and stuff, but we can make antibodies against things in the lab. So you inject an animal with something you want to act as an antigen, or the thing that the antibody will bind to. And then they make antibodies, and then you test and see the antibodies for the thing that you wanted them to react to. And the reason why this is helpful is because you can then use these antibodies for various things. So sometimes you can have like something attached to them that you can then detect, or this. So this is for a different. This is when I was talking about blood typing, but the concept is similar in terms of some of the assays use this like agglutination reaction. So basically like a clumping up reaction. So if you have the antibodies to it that get stuck to that, and then you add this thing that'll bind to the antibodies and get everything to clump up, and then you measure how like clumpy it was. Enzymatic methods, we actually like cut off the sugar that you added. So, and then, and so for those antibodies, they typically like raise antibodies against this, and then they like react to just specifically this glycation product. For enzymatic methods, typically they like have things that'll cut off the glycation, and then they have like enzymes that'll react with those products and then give a signal. So there's a bunch of different ways that it's done, but then they're all like kind of standardized and into like this weighted average value. Okay, and now it's time to get into the really, really geeky stuff. So OChem fans, hope you like this, and everyone else, you're probably able to tune out, or you already have, but you're happy to follow along. And hopefully I explain everything okay.
So in your body, glucose typically exists in its ring form, and so it has two different like stereoisomers. So if you look at this group, when it forms this ring, basically this OH is going to attack this carbon, and this is going to, so this O is coming from here. But depending on what direction it attacks from, you'll get this OH up or down. And we call this like the chair conformation when we draw it like this. So we'll be using this form later. But basically, glucose can interconvert between this form, the alpha, and the beta. So you can see the differences here, whether this is up or down. And in order to get between these, it has to pass through a linear form. And so this linear form isn't very common. It's kind of like a transient intermediate most of the time. But it's the form that's going to be reactive, because here you have this free aldehyde group, and this lets it act as a reducing sugar is what we call it. But basically what you need to know is it has this this aldehyde group, so it could C double bonded to an O and a hydrogen. So I'm gonna simplify this drawing so hopefully that you can see that what's going to be happening is mainly going to be in this part. So this part's this. Then you have 3 of these CH3OHs. So in this form, we're not caring about stereo chemistry or anything. So which direction things are pointing in space, we're just going to worry about this. And so this is just like a shorthanded version of it. And so we're just going to be focusing on this part here. So this is going to be where our glycation is going to come from. So all of these are just different representations of glucose. And glucose is going to be what we're going to be adding, but we're going to be adding it and then like changing the form. So it's going to react with the N terminus or the end of a lysine chain. So the N terminus of a protein or the end of a lysine chain. And what these have in common is they have this amine group. So typically it's in like the NH3 protonated state, but it also exists, it needs to be in like this deprotonated state in order for this reaction to occur. And why that is because in the deprotonated state, now nitrogen has this lone pair of electrons, and this lone pair of electrons is going to be nucleophile. And then this carbon is going to be our electrophile. So this is because, a nucleophile is something that that once, like a nucleus, so it wants protons, it has more electrons, it has electrons it can share, or it has electron density, it wants help carrying. And then electrophile is something that wants electrons. And so this carbon attached to this oxygen, these oxygens, although this is neutral, these oxygen is going to be partly negative, and this carbon is partly positive, because the oxygen is electronegative, and it's pulling electron density away from the carbon, making it electrophilic. So the nucleophile, when you have a nucleophile and an electrophile, they can react. And so this is what we're going to see. So the first step is the formation of a Schiff base formation. Another name for a Schiff base is an imine. And amine is like end attached to, so like NH, H, or whatever, or it could be ends with carbons or whatever. Those are all amine groups. When you have an imine, you have a nitrogen attached, double bonded to a carbon. And this is going to be like very reactive. Okay, so when we have this, we have our nitrogen with our lone pair. This is going to be our nucleophile. If we do, it's going to attack this electrophile, and this is going to push these electrons onto the oxygen, breaking this single bond. So what this is going to give us is we're going to start with like a charged intermediate. So we're going to have carbon bonded. So now we have a single bond here. And because we gave those electrons to the oxygen, now this is negatively charged. This is going to be COH, H. Okay, I think I'm just going to abbreviate this part here. We're just going to abbreviate it with what was the coloring I used before. We're just going to abbreviate that with orange. We're just going to be focusing on the red stuff. So we're just going to be focusing on this part, so I don't have to keep writing all that out again. Okay, but at this point, so now we don't have this attached to the H, though. Now it is attached to the nitrogen, but the nitrogen is still attached to two hydrogens, as well as to the rest of the chain. And so at this point, the nitrogen is going to have a full positive charge, and the oxygen has a full negative charge. This carbon does still have a hydrogen. Sorry about that. Okay, so then you have this intermediate. So you can see you have this separation of charges, and this isn't very stable. This oxygen would much rather have this proton, and this nitrogen would much rather not have this proton. So we get a rearrangement, a little proton shuffling. And this is all like, these steps are reversible. And so you end up with this, I think, an OH, H. So now you have your NH back. So now everything is happier. But we don't have our Schiff base yet. We just have a happier thing. And what this is called is a hemiaminal. This is a hemiaminal. And the next step is we are actually going to form the Schiff base. And in order to form the Schiff base, what's going to happen is this oxygen is actually going to get protonated. So you have some acid, we'll just call it H, we'll just put an H plus. This oxygen is going to take that, and this is going to give you COH. this as a positive charge now, and okay, there we go. Okay, so now we have this chart. This is now a good leaving group, and so this can leave as water. So what's going to happen is this lone pair of nitrogen, it is going to add back to this double bonded here, make a double bond with this carbon. That would give carbon 5 bonds. Carbon can't have 5 bonds. So this comes, leaves, and this leaves is going to leave as water. So then we are going to get our C double bonded to our nitrogen, hydrogen. Okay. This has to be positive now. So we've lost water. We started with the charge thing. We need to keep that charge, and that charge is now going to be on the nitrogen because it has 1, 2, 3, 4 electrons assigned to it, and it has 5 protons. And so it's going to have a positive charge. And so this part we have inium, ion, or a charged Schiff base, or a protonated Schiff base. Sorry, I'm like filming one-handed, so I can hold my camera or hold my phone. Yeah, obviously not set up for this. Okay, and so at this point we have the protonated form, and then all that's needed is for this to deprotonate. So if you have some base, H minus, base can come, take that proton, leaving you with your final product of C, H, N, and then all the rest of that. Okay, so at this point we have our Schiff base. So at this point the nitrogen still has this lone pair. So it's still, this is reversible. So everything up to here is reversible. And so we can actually, this can get like hydrolyzed, and you can go back to having this like swapped out for a carbonyl. So have this turn into an oxygen again, and that would release all of the glycan. But that's not going to happen, because what's going to happen is this is going to undergo an amidori rearrangement. And what that's going to do is it's going to take the double bond that was on the nitrogen, and instead we're going to end up with a single bond to the nitrogen. Single bond to the nitrogen. Sorry. And this is going to, we're going to have our double bond to this oxygen instead. So so we're going to end up with, now we've shifted our double bond to this oxygen, so this is now a ketone. So before it was an aldehyde, so when we initially had our glucose, this is an aldehyde because it had this double bond O to an H. Now we have a ketone because we have a double bond to an O with carbons on either side, so it's like in the middle. And remember, all of this is the rest of the glucose. So all of this, so this part, this is all happening. We have this, the Schiff base formation and everything is happening when glucose is in its linear form. But then it's actually going to change back into its ring form. So if we draw out the whole thing again, so if we have so we have basically it attached CH. We have this, and then we have, if we go back in that whole oh sorry, yeah, so when I had we also here we had the blue and the orange, we were kind of combining down here. So if we redraw all that out, we now have CHHO. Oh, and this paper or whatever, I'm not endorsing, I don't even know what the product that is on this thing. It just happens to have given me a notepad when I went to a conference a long time ago and I needed some paper. So okay, so now we can freeform the ring product. So when it undergoes this rearrangement, so all of that's happening when it's in this linear form, but then it's actually gonna like close chain again. And when it does this now, instead of coming from this group like we did before, we're gonna come from this N group. And now remember we have this ketone. Before we had the aldehyde when we were starting out doing that like circularization of glucose before. We had this aldehyde, and now we on this, like, so it was on the end, our carbonyl was on the end, and now it's here, but it still acts as an electrophile. This oxygen has a lone pair of electrons, so you get this ring formation here. But now you can see that you have this. So if we started with, this was our glucose, and now this is what we end up having attached. So you can see that the linkages is different, as well as, like, you don't have this CH2 here because this is actually the oxygen, so this one's going to be like reacting. And so, but anyway, so you end up with it back in a circularized form,